Welcome to Math 106, Chapter 1.7. We're talking a little bit more about derivatives. So now that we've been using variables such as x and y a little bit more often, we can actually use any variable that we like. So when we're asked to differentiate d of dx for x squared plus x minus 1, we are deriving only your x values. So if we use variables instead like t, it would be just as the same way we would do it just with x. Now keep in mind your bottom variable is the one that is being differentiated. So if we had an expression like this, d over dA, which variable are we meant to derive? Well, we're meant to derive everything in terms of a. So you're going to treat this expression as if B isn't so much as a different variable, so much as we're looking at A to be the one that we're deriving. And so nothing else really matters number or numerically. So if we're taking a look at this one, right, notice that we have 2a cubed times b, right? A times b times 2. So we're still going to apply your same rules. So still push down your 3 here and multiply. So we get 6a, right? And then b, because b is still acting kind of as like a coefficient for a, it's still going to get tacked on. Whereas b again, you're deriving in terms of a because there's no a value to it. Let's say there was, let's tack on an a. How would you derive a? Well, deriving a for this particular term, right, we could drop the a because it has a degree of 1. Therefore, it's just b. But because we don't actually have this a term here, it's just b. B is acting as its constant. So when it's the constant, right, we drop it. It's just b. So this would be our answer if we derive just in terms of a. Whereas if we derived it in terms of b, what would we get? Well, for us being deriving in terms of b, so notice that in this term, right, b is the term that we want to derive, or b is the variable we want to derive. So b has a degree of 1. Therefore, we can just drop it all. And we're left with just 2a cubed for this term. And then again, b has a degree of 1 here. So we get left over with 1. The 1 comes from your coefficient of b. So it just gets dropped off. We have a cubed plus 1, which is your derivative. Now let's try it again with the next few examples. So see if you can pause the video. We're still going to be practicing a lot here. So you have d over dt. So we are going to derive every term in terms of t. So let's take it in chunks. Look at this term here. How would you derive this term? Deriving with t. Well, we could drop here 2. So we now have 2 times a times t to the first power. You still with me? Now let's look to your next term. When we drop, we drop the negative and then subtract the 1, right? Just like we did here. Drop the negative 1, s, t is now to the negative 2. Now this one, because it does not have a t, right? This is now acting as your coefficient. So you could say plus 0 or just leave it off entirely. Now, I don't like the look of us having a negative exponent, so let's finish it off by making everything nice and simplified. We're going to just drop it down low. And if you wanted, you could just say that this is your constant. We'll just remove it all together. This is your constant. Very much like if we had 3x plus 4, right? Notice that the 4 doesn't have an x value to it, right? So when we go to derive, it would just be 3, right? The 4 just disappears when you derive. Let's try it again. Now, this s up here is just referring to this equals, just like if we had dy dx, it's it's your variable that you're doing it in terms or as a function of. So for here, we are still deriving p with respects to s. So the s doesn't matter. We're going to look at all of these and think about how we're deriving p. Now, p is locked into this parentheses here, which think about what we learned from your that general power rule. It's really the chain rule, like the very elementary basics of this chain rule, which if there's something inside that we want, right? We talked about last time, you're going to a museum, maybe you see there's I don't know, like a sarcophagus, like a mummy sarcophagus in a case, and you really want to touch it, right? You're just fascinated. You just want to know what it is. So it's in this case, and in order to touch it, you have to break open the case. Same idea here, this being the mummy on the inside or the case or whatever you have it, right? We need to take care of the power first, right? You need to knock down your barrier. So to derive, we first need to apply the power rule. So power rule says, okay, we're going to multiply 3 times 10. We're going to keep the inside the same, right? You've just knocked down the barrier. You've just knocked down the case. You broke it open. And now you actually go ahead and get to touch or take the treasure, whatever it is, right? Then you get to go ahead and derive the inside. So that would be deriving your inside. Make it look a little bit nicer. We get 30p squared plus 5p plus 1 times 2p plus 5. So now let's take a look at the second derivative. So if we take the derivative of f of x, we end up with the first derivative, or f prime of x. If we take another derivative, then we end up with f double prime. So we do this by taking your first derivative and deriving it once more. So see if you can pause the video for example 2 and take your first and second derivative of your following. So here, right, your first derivative, we get 3x squared, and I'll just rewrite this term to show the power. So we drop down the 1, we now have x to the negative 2. So that's your first derivative. Again, a different way to write it would be to then get rid of your negative exponent by dropping it down. Your second derivative, we're going to take your first and just derive it once more. So the 2 comes down, subtract the 1. So you get 6x minus, and then drop the 2 down. So that's negative 1 times negative 2, x to the negative 3. Again, just subtract the 1, just kind of showing some of your work down here. Drop, drop. So we get 6x plus 2x cubed, or again, a better way to write it, 6x plus 2 over x cubed here. Let's try it once more. So f prime of x is equal to just 2. 1 is a constant, so we no longer need to work with that one. I'll just write that there. So now let's go ahead and derive. And in case maybe I need to show an extra step, let's say we have your 1 up here, and after you bring it down, right? So then you're multiplying 2 times 1 times x to the 1 minus 1, which is then 0. X or anything to the 0 is just 1. So you're just left with 2 because this all equals 1. So now let's just say we had 2, right? And we're still deriving in terms of x. It's now your constant. So this one, your second derivative is 0. All right, once more, your first derivative. Let's go ahead and bring down the 1/2. Subtract 1 from 1/2. So that would be 2 over 2. So that's negative 1/2 plus, and actually this is minus because we're going to bring down a negative 1/2 this time. And again, subtract 2 over 2. So you're now at negative 3 over 2. And again, a better way to finish off this derivative, we could write it as 1/2, actually even better, 1 over 2t to the 1/2. And again, this kind of rule, if it starts as a fractional exponent, you can end in 1, but you would definitely want to make it positive. Same thing over here, 2 to the t to the 3 over 2. And there you go. Let's do it again with your second derivative. We'll bring down the negative 1/2. So that makes 1/2 times the negative 1/2. That would be the negative 1/4. Subtract another 2 over 2. So that one turns into that 3 over 2. Plus, and again, this would be negative 1/2 times 3 over 2. So that would be, and that's a negative, plus 3 over 4 t, and again, subtract 2 over 2 here. So then we get negative 5 over 2. And again, a better response would be negative 1 over 4 t to the 3 over 2 plus 3 over 4 t to the 5 over 2. So those are your examples for example 2. Now let's get familiar with some of your notations. So if we're talking about prime notation, right, you could have f prime of x or y prime. That's just your first derivative. You could also say f double prime or y double prime, right? There's just 1 versus 2, right? The equal opposites would be if we're looking for d over dx, right? Derive f of x in terms of x, or this one, dy over dx with respects to y, derive x, or f double prime. Notice that we now have these little squared. You're going to take the second derivative of x, or take the second derivative again of x with respects to y. That too just suggests that we're taking the second derivative. So take, they're all over, aren't they? Take the second derivative. So note that d squared over dx squared is purely symbolic and does not mean d squared over d times x squared. So it's like not a logical thought. It's just symbolic. So instead, it's just asking you to take the derivative twice. It does not mean that you're going to square anything. It's just a way to say take your second derivative. Another notation here is that you have dy over dx, given that x is equal to a. So it's just saying that after you've derived, we want when x is equal to a. So this just says, first derive x, then find when x is equal to a. Therefore, all you need to do is substitute when x is equal to a. A for x, that's a better way to say it. Whereas this one, it could say f double prime of a, or another way to say it, take the second derivative of x and then substitute an a. So those are kind of the new notations. So let's have you try example 3, given what we now just talked about as far as notations go, and then what to do when we have x is equal to a value. Now, what does example 3 mean? Well, it wants us to take the second derivative of x, and then once we finish it, we are going to look for what that value is, given that we have x is now equal to 3. So let's see if you can pause the video and work that one out. We're looking for the second derivative, and I'll just do of y. It's equal to 4, so sorry, your first derivative of y is 4x cubed minus 15x squared, and then that 7 drops off. Now your second derivative should be 12x squared minus 30x. Now that you've taken your second derivative, we are going to substitute when x is equal to 3. So we are going to replace x with 3. So I'm going to swap f of x for, or sorry, y for f of x. So now let's go ahead and plug it in. We have 12, 3 squared minus 30 times 3. So that's 3 squared, which is 9. So 12 times 9 minus 30 times 3, that's 90. So then 108 minus 90 will be 18. And there you go. Now the derivative as a rate of change. So recall that your derivative is the slope of the tangent line, and the slope is referred to as the rate of change. Thus, if we're looking at f prime of a, this is the rate of change of your function when x is at the value of a, is at a particular point that you've selected. So as the graph of your function, f of x, is going to the point P, it is changing at a rate, and that is your slope, right? This is just another way to say that this is the slope. So it's changing at the slope in units in the y direction for every 1 unit change in x. Therefore, and notice that it emphasized the every 1 unit change in x. Therefore, as a rate of change, so derivative as approximate rate of change for the increase of 1 unit. An increase of 1 unit is given by this particular formula. This is called kind of like the marginal cost concept. So to approximate the quantity, of C of A plus 1 minus the original C of A, the plus 1 is just the additional increase of that unit. We want to know how much will it cost us to just give us 1 more unit to produce, right? So from going from what we have now to 1 additional, it's going to give us this approximation. So marginal cost is the slope of the tangent line at that value. It is the approximate cost by adding 1 more commodity. So really your derivative, your first derivative is marginal cost at that production. It is the same as if we're discussing revenue and marginal revenue. Revenue being, okay, this is the original, and this is the cost of adding just one extra, or the how much is gained after one extra. Same thing with profit and marginal profit. So take example 4. It says, suppose the revenue from producing and selling X units of a product is given by your formula. So we have R of X is equal to X, or 11X minus 0.02 X squared dollars. Find the marginal revenue at a production level of 35. So they're telling us that X here is going to be equal to 35. But because we're talking about the marginal revenue here, this is really interested in one additional cost, or one additional increase. So if we're given R of X is equal to 11X minus 0.02 X squared, to get the marginal revenue, we can take your derivative, right? To go from one to then another, we're just taking your derivative. So we should get 11 minus 0.02 times 2 X, which is equal to, when we fix it up, 11 minus 0.04 X. So this is what it would be when this is kind of the slope of that tangent line of your revenue, right? To increase the additional revenue. So let's say we have 35. So we can now substitute when X is equal to 35. So the increase in production of an additional unit, oops, 11 minus 0.04 times 35, there we go. We're going to increase in $9.60 for the additional unit. Now let's say we want to find the production level where the revenue this time is equal to 500. So if we know that your revenue is equal to 11X minus 0.02 X squared, we also want that your revenue is equal to what? Well, it's equal to $500. Well, where is it that this is equal to $500, right? If they're both equal to R of X, that must mean that they are equal to one another. 500 is equal to 11X minus 0.02 X squared. Have we seen something like this in the past? Absolutely. And notice that we have a negative quadratic. So let's make everything to go onto one side. So let's subtract everything, or add everything on the right-hand side. So let's go ahead and do that. So we have 0.02 X squared minus 11X plus 500 is equal to 0. Now, what did we do from here at this particular point? Well, if it's not factorable, then we can always use the quadratic formula, which the quadratic formula, when X is equal to negative B plus or minus the square root of B squared minus 4AC all over 2A, where A is equal to 0.02, B is equal to negative 11, and C is equal to 500. So we can go ahead and work that into your equation. We have a double negative for your B. When we work it in, we're still going to be using parentheses because as we've talked about, that makes a big difference. We do have your calculators at hand in our classroom. So we should get 11 plus or minus the square root of 121 minus 40 all over 0.04. which is equal to 11 plus or minus the square root of 81 all over 0.04. So 11 plus or minus 9 over 0.04. Now, when we go to do this, right, we want to figure out, right, where is your production level at 500? And this is because it's a quadratic, right, what we're really looking for here, let's say a quick visual. There we go. We want to know, let's say this is your 500 mark, which that's actually a terrible picture of this. There we go. Let's say this is 500. I want to know these particular points. I have my y. I need to know these x values that correspond with it. So x is equal to either 11 plus 9 over 0.04 or 11 minus 9 over 0.04. Those came out nicely. So between when your X units are between 550 units, will your revenue be at $500?